Have you ever found yourself wondering how Netflix just knows what movie you're in the mood for? Or how Amazon can predict shipping times with such scary accuracy? Well, I can tell you, it's not a crystal ball. It's math. And today, we're going to open up the very toolbox they use. We're talking about probability distributions. These are the incredible tools that help us see clear, predictable patterns in what seems like total chaos, allowing us to make some seriously smart predictions in a world that is, let's face it, pretty uncertain.
I mean, really think about it. Picture a store manager trying to stock up for the holidays, or an airport manager who is just desperate to keep flights on time, or maybe a factory that has to promise its products are top quality. They're all wrestling with the exact same massive question. How on earth do you predict the future? Well, the answer is right here, in the tools we're about to lay out. And let me be clear, this isn't some dusty, abstract theory. This is the real, practical engine that's driving smart decisions in business, in science, and logistics, you name it. So, here's our game plan for building out this toolkit. First things first, we've got to understand the two main types of data we'll ever come across. It's the foundation for everything. Then, we'll start adding our first set of tools. These are for counting things, whether it's something common or something super rare. After that, we'll grab a whole different set of tools, and these are designed for measuring things like time or distance. By the time we're done, you're going to have this amazing, versatile starter toolkit ready to make sense of all kinds of real-world problems.
All right, let's dive in. Before you can build anything, you have to understand your materials, right? Well, in the world of probability and statistics, that means knowing the absolutely critical difference between two types of data. I'm telling you, getting this one distinction right unlocks everything that comes next. So on one side, we have what's called discrete data. The simplest way to think about this is anything you can physically count, like the number of customers who walk into a store, the number of defective items on a production line, or the number you get when you roll a pair of dice. You can have 10 customers or 11 customers, but you can't have 10.3 customers, right? The values are whole, separate, countable numbers. That's discrete. Then, on the other side, we have continuous data. This is anything you have to measure. Think about the exact time it takes to finish a race, the temperature outside, or a person's height. These things can take on any value within a range, down to an infinite number of decimal points if your measuring tool is good enough. Our toolkit has awesome, specialized tools for both of these. Okay, so now that we've got that counting versus measuring thing down, let's reach into our toolkit and grab our first tool for counting. And honestly, this one is a real workhorse. It's the one you'll use all the time because it's built for any situation that boils down to a simple yes or no answer. Think pass or fail. A customer buys or doesn't buy. An email is spam or not spam.
And here it is, the binomial distribution. This is your absolute number one go-to tool anytime you have a situation that checks a few key boxes. First, you need to have a fixed number of trials. Second, each of those trials has to be independent. What happens in one doesn't affect the next. And third, every single trial has only two possible outcomes. Now, we usually call them success and failure just to keep it simple, but it could be anything, heads or tails, click or no click, defective or not. It is unbelievably useful.
Whoa, okay, I know what you're thinking. A formula. But stick with me here. I promise this is way more intuitive than it looks. Just think of it like a recipe with a few key ingredients. That px equals x on the left, that's just a fancy way of asking the question, what is the probability that the number of successes I'm looking for is exactly this number, x? Simple. Now for the right side, the actual recipe. N is just the total number of trials, how many times you flip the coin, how many customers you look at. P is the probability of a success on any one of those trials. And Q? Well, Q is just the opposite. It's the probability of a failure, which is always, and I mean always, just 1 minus P. See? Not so bad. Now for the secret sauce, that little NCX part. This is called the combination formula, and it's a powerhouse. It automatically calculates all the different ways you can arrange your successes within your trials. It's what makes this tool so smart.
All right, enough theory. Let's put this amazing tool to work. Let's go back to that store. 3 customers walk in. The manager knows from experience that any given person has about a 30% chance of buying something. So the big question is, what are the odds that exactly 2 of those 3 people make a purchase? Let's plug it all into our formula. Our number of trials, N, is 3 for our 3 customers. The number of successes we're hoping for, X, is 2. The probability of success, P, is 0.3. That means the probability of failure, Q, is 1 minus 0.3, so 0.7. Now let's do the math. First, that NCX part, which is 3C2. The formula for that tells us there are 3 different ways 2 out of 3 people can buy something. Next, we take p to the power of x, so that's 0.3 squared which is 0.09. Then we take q to the power of n minus x, so that's 0.7 to the power of 1, which is just 0.7. Now we just multiply all those pieces together. 3 times 0.09 times 0.7, and that gives us 0.189. So there is an 18.9% chance that exactly 2 of the next 3 customers will buy something. See? That's not a guess, it's a precise, data-backed prediction.
And this is where it becomes a real superpower for businesses. The binomial distribution isn't just for one-off questions. It makes forecasting so much easier. To find what we call the expected value, basically the most likely outcome over the long haul, all you do is multiply the number of trials, n, by the probability of success, p. So, if our store is expecting 1,000 customers next month, they can reliably predict around 300 sales. And that's how you go from just guessing to making really smart strategic decisions about how much inventory to order, how many people to have on staff, the whole 9 yards. Okay, our toolkit is starting to look pretty good. The binomial is fantastic, but it has one big condition. You need a fixed number of trials. So what happens when you don't have that? What if you're just interested in counting how many times something happens over a stretch of time or across a certain area, especially if that something is kind of rare? Well, for that, we're going to need a brand new tool. Meet the Poisson distribution. This is the perfect tool for counting occurrences over some kind of continuous interval. I'm talking about things like the number of emails that hit your inbox per hour, or the number of typos on a page in a book, or maybe the number of cars that pass a certain point on the highway in a minute. In all of these cases, we're just counting how often something happens within a given block of time or space. It's a really elegant tool designed for exactly this kind of problem.
And believe me, once you know what to look for, you will see the Poisson distribution running things quietly in the background absolutely everywhere. It's helping airports schedule plane arrivals so you don't have chaos on the tarmac. It's helping call centers figure out how many people they need working the phones during peak hours. Factories use it for quality control. Banks use it to predict how many customers will show up so they can open the right number of teller windows. I'm telling you, anytime you're dealing with arrivals or occurrences in a system, this is probably the tool being used.
So let's peek under the hood at this thing. The P of X is still what we want to find, the probability of seeing exactly X events. But the key new player here is that Greek letter, lambda. Lambda. Lambda is wonderfully simple. It just represents the average number of events you typically see in that interval. So if you get, on average, 10 emails an hour, your lambda is 10. E is just a special number in math, kind of like pi that pops up everywhere. It's roughly 2.718. And x factorial is what we call x factorial, which just means you multiply x by every whole number smaller than it. The real beauty here is that if you just know the historical average, if you just know lambda, you can use this simple formula to calculate the probability of any other number of events happening in the future. It's pretty much a mathematical crystal ball.
And here is that super elegant secret I mentioned before. This is what makes the Poisson distribution so unique and powerful. Its mean, lambda, is also its variance. Now, variance is just a fancy stats term for how spread out the data usually is. For almost every other distribution, you have to figure out the average and the spread as two separate things. But with Poisson, it's a 2-for-1 deal. If you know the average, you automatically know how much the numbers tend to vary around that average. It's an incredibly efficient and clever property. Now, before we switch gears from counting to measuring, let's add one last specialty tool to our counting kit. It's called the hypergeometric distribution. The best way to think about it is as a cousin to the binomial, but it's for those situations where you don't put things back after you draw them. With the binomial, the probability P stays the same for every trial. But with hypergeometric, every single draw changes the odds for the next one. The classic example is drawing cards from a deck. Once a card is out, it's out, and the whole deck has changed. Or imagine inspecting a small batch of parts from an assembly line and setting each one aside. For those no second chances scenarios, this is the tool you need. Okay, team, we've got a great set of counting tools. Now, let's flip open the other side of our toolkit and check out the tools for measuring. Remember, this is when we're dealing with things like time, distance, weight, temperature, stuff that can take on literally any value within a range. For this, you need a whole different class of instruments.
Let's start with the simplest, most straightforward measuring tool we have, the uniform distribution. Just like the name says, you use this when every single outcome in a given range has an equal chance of happening. No single outcome is more likely than another. If you were to draw a graph of it, the probability would just be a flat straight line, forming a perfect rectangle. That's actually its nickname, the rectangular distribution.
So let's imagine a flight. We know from history that this particular flight takes somewhere between 120 and 140 minutes. Any time in that window is just as likely as any other.
So what's the probability that the flight lands in the first 10 minutes of that window, between 1:20 and 1:30 minutes? Well, with the uniform distribution, the calculation is incredibly easy. You just take the size of the window you're interested in this case 10 minutes, and you divide it by the size of the total possible window, which is 20 minutes from 1:20 to 1:40. So 10 divided by 20 gives you 0.50. There's a 50% chance. It's really that simple. Okay, next up in our measuring kit is a real specialist, the exponential distribution. This one is all about weighting. Its entire job is to help you predict the amount of time that will pass between events. Questions like, how long until the next customer walks in the door? How long will this phone's battery last? How much time until the next bus shows up? For any question that starts with how long until, this is almost certainly the tool you need.
And this is a really cool moment. This is where it all connects. It turns out that Poisson and exponential are like two sides of the very same coin. Let's go back to those cars arriving at a petrol station. The Poisson distribution helps you answer the question, how many cars will show up in the next hour? The exponential distribution answers the question, how long will I have to wait for the very next car to arrive? They work together. They're a dynamic duo, mathematically linked, that gives you a complete picture of any process involving arrivals over time. One counts the events, the other measures the time between them.
So let's just pause for a second and take a look at what we've built. In a pretty short amount of time, we've put together an incredibly powerful, foundational probability toolkit, literally from the ground up. With these tools, you are now officially equipped to start modeling, understanding, and making real predictions about a huge variety of challenges you'll see out in the world.
You see, the most important takeaway here isn't just memorizing the formulas. It's having the mental framework. The next time you're faced with a problem that involves randomness or uncertainty, you can just ask yourself a couple of simple questions. First, am I counting something or am I measuring something? Second, are the events independent or do they affect each other? Just answering those basic questions will immediately point you to the right tool for the job, every single time. Now, our toolkit is seriously impressive as it is, but I have to be honest, there's one more giant out there, a tool so important and so common that it's often called the father of all distributions. I'm talking about the normal distribution, which you've probably seen as the famous bell curve. It shows up everywhere in nature and data, but that's a much bitter story and one for another day.
So here's my challenge to you. As you go about the rest of your day, try to see the world through this new lens we've built. When you're standing in a queue, think about arrival rates. When you're waiting for a bus, think about the time between events. Look at the world around you and see the hidden patterns. Because with this toolkit in your back pocket, you're no longer just a passive observer of random chance. You are a predictor. The only question left is, what are you going to predict first?